Well, thanks everyone for coming today. We're delighted to welcome you to the annual meeting for the US-Asia Technology Management Center at Stanford. I'm Richard Dasher, I direct the center, and what we'll do today is first we'll have our keynote address. Then I'll give you an overview of what we've done for the last year and what we plan to do for the next year. And then after a brief break, we'll have presentations by 6 of our visiting scholars, some of whom are here and some of whom are remote joining us by Zoom. So welcome to everybody on Zoom and also to our friends here. I'm delighted today to be able to welcome Professor Zhenan Bao, who is the KK Lee Professor of Chemical Engineering at Stanford. She's also a professor by courtesy in the departments of Material Science Engineering and Chemistry. She is also the founding director of the eWear initiative, the Stanford Wearable Electronics Initiative. Her work for a long time, we've known each other for a long time since she's been at Stanford, has been on flexible electronics for semiconductor circuits. And from this, she decided to found this eWear initiative, which is incredibly timely and looking at applications in many different areas. Her PhD is in chemistry from the University of Chicago. She went to a place that kind of no longer exists, right? Bell Labs, and became recognized as a distinguished member of the technical staff in 2001. She joined the Stanford faculty in 2004. She has been named to the American National Academy of Engineering, the American Academy of Arts and Sciences, the National Academy of Inventors. She has over 700 refereed publications and over 80 patents that she has produced during her career. She is also the founder and board director of 2 companies here in Silicon Valley, C3 Nano and Pyramids. So I think that I should turn over the floor to Professor Bao and ask her to talk about electronic skin.
Okay, thanks, Richard, so much for the invitation to speak. Richard mentioned that we got to know each other when since I joined Stanford. Actually, Richard was one of the first few people I interacted from outside the chemical engineering and gave me some very helpful tips that actually inspired me to think about eWear and different kinds of programs. So my group has been working with really thinking about what future electronics are going to look like and what we will build from actually bottom up and also from molecular level, because I was trained as a chemist. And the reason we're interested in such a problem is that if you look at the kind of electronics we have today, they are already amazing. They allow us to access information anywhere, anytime. But on the other hand, if we look at the electronics that are used to understand or monitor human health, or to really understand human health, or for treatment of diseases, they are very primitive. They either don't allow us to get enough information, or they are still based on very chunky and really rigid electronics and bulky electronics that are very difficult to interface with human beings. So we thought that, well, also at the same time, there is the great need to really understand human health or being able to catch disease before they even develop any symptom. So precision health, precision medicine is basically when there is a disease, doctors will develop a treatment that's individualized. But precision health, what it means is to be able to have a baseline of health for everybody so that we know how our health is developing and catch a disease before it's even developed. And that means that we can not still continue the current paradigm of measurement or diagnosis, which is go to a hospital once a year and get your blood sample taken and then perform all kinds of measurements. But rather, we need to basically take the measurements on the human body directly and have this information available and continuously be able to monitor such information. And also from the point of view of understanding human health, that means we need to understand how different kinds of signals that regulate human health. That include electrical signals and also various chemical signals. For example, hormone, they impact our mental health, our stress level, our digestion, and electrical signal regulates the brain, but also that in turn regulates our heart and muscle and intestine movement. So all of this information, they are all related. But then currently, we can only measure such information in a very localized region at one spot, potentially on the human body, whether it's just one part of the brain or one part of the heart. But these signals are actually generated at high resolution. That means cellular resolution of few micron to tens of micron. Human hair has a diameter of 100 micron. So that means the cellular level is slightly smaller than the hair diameter. That's much bigger than the current state of art of the integrated circuits. But it's a range that's very accessible for many new technologies that are emerging and that are being developed. But at the same time, that's high resolution I'm talking about. Only need a micron or tens of micron. But at the same time, we want to measure this information over a large area and without disturbing the human behavior. And then we would be able to really understand from the science point of view how these different signals really impact each other from the brain, how the brain controls our movement or even language, or how the intestine, the gut, we talk about gut feeling, how does the intestine, microbiome and motility impact the mental health and vice versa. So that's what we are interested in. But if we look at today's electronics, as I mentioned, they are built with rigid materials. So these rigid and brittle materials, they give us electronics that are also rigid and brittle. But to realize our vision of understanding human health and also bring the lab to the human, we need electronics that are comfortable, invisible, imperceptible, biocompatible, and also autonomous. So that's really the bigger picture we have. And then we thought that in order to do that, if we use human skin as the inspiration, thinking about human skin, you think about this essentially as a chemist or a material chemist. I think of it as a material. Human skin is a material that's soft, that's flexible, stretchable, biodegradable, and can even heal itself when there are damages. So what if we can make electronics that looks like skin, feels like skin, and have the sensing functionalities just like human skin, and have the signal processing ability like human skin? When we touch things, our skin actually converts the touch information into electrical pulses and then go to our brain for processing. So all these are the essential components we would want to have in our sensory devices or implantable devices. So if we can build this electronics that it has all the attributes of human skin, maybe we can really change how humans interact with electronics in the future. So that's what we have been working towards over many years. And this picture here you're looking at is not our latest electronic scheme, but it represents very well the form factor we're trying to build in. It contains integrated circuits that are already at decent speed that we can start incorporate into the sensory systems. I'll show you some examples of where we are. So as a chemist, I think from molecular level, and I believe that by designing the right molecules, we will be able to get conductors, semiconductors, and dielectric materials that are needed to build this new form of electronics. And what we need is basically materials that are as soft as jelly, and but have electronic performance like integrated circuit, not the really the fastest speed integrated circuit we have today. I think it will be difficult for us to realize that, but electronics that has moderate performance amorphous silicon or polysilicon level, then we will be able to do many things. So that's the goal that we set. And without going into too much details, basically from the scientific point of view, I talked about we have to think about molecules and we have to make them conductive and also semiconductive. The way we do that is to really engineer molecules that are very rigid, and they can allow charges, electrons to transport along these rigid backbone. At the same time, these electrons also have to jump from one molecule to another, and then we design them so that then they have these pathways that can allow the charge transport. But then that also poses challenges to our materials design. That is, it gives us also, even though these are plastic materials, they are also rigid, can also crack when we try to strain them. And on the other hand, we also have rubber band materials, elastic materials we use in everyday life. Actually, on the molecular scale, those materials normally have a very flexible, like spaghetti-like molecules. But then those molecules will not be able to conduct electricity well. So my fundamental study and challenge is really how do I solve this kind of conflicting requirements in molecular design and really come up with the right design, then I can have best of both worlds. So that's the kind of research that we do. And then we had a breakthrough 6 years ago that we found a number of molecules that worked well, but then the breakthrough really came by when we found the ways to really induce these nanostructure formation in our electronic material. And then this was formed. The good thing is it's formed when we introduce another matrix material that is either elastic or biodegradable or self-healable. Basically, we have this matrix that has the desired skin-like property. But then this matrix, once it's introduced with our semiconducting material or conducting material, it makes our originally brittle material to form nanostructures and then force them to align really well along the long axis of the nanostructure. And this actually, to our surprise, not only allowed us to add a new property to our electronic material, but at the same time actually boosted the electronic conductivity or in the semiconductor, the charge transport actually significantly, and address the long unsolved challenge that my field has been facing in terms of getting rid of all the disorder in these materials. So that was a crucial discovery that we made, then allowed us to now have a variety of materials, whether it's conductive or semiconductive, and then added all the skin-like stretchability, self-healing, and biodegradability as the combination. So for example, in the conductive material range, now we have a stretchable conductive material that's as good and also semi-transparent, similar as if you come from display or semiconductor industry. Indium tin oxide is the kind of typical material that's a transparent and a conductive that's used for display. Now we have a stretchable version that's transparent and a similar conductivity as indium tin oxide, but stretchable at the same time, using a kind of a molecular design that we add all the components we need into the conducting polymer and form those nanostructure. Then we can have all the new properties we want. Not only these are important for making electrodes for integrated circuits, but these are also electrodes that can allow us to measure brain electrical signal, muscle electrical signal, heart electrical signal without constraining the movement of the body or without damaging the brain tissue, because these are very soft materials, so just as soft as brain. And just for the fun of it, I have a colleague in medical school who wants to study the neurons on octopus. But then it turns out the octopus, even if you give it anesthesia, do you know what kind of thing is used to make octopus sleep? Alcohol. The same as for humans. They just give octopus some alcohol, then the octopus will be sleeping, but still the arms, the legs are moving around, so they couldn't measure anything when they used the rigid electrodes. And then we put on our soft electrode because it can move with the legs, and we were able to record high density electrical signal from this. Okay, and then not only that, the same concept now allow us to develop kind of conductors, semiconductors. So we apply it to light emitting materials. It can also enhance the brightness from the light emission. So now we have all the materials to also make this type of new form of deformable display that you can imagine interactive display. If you touch the surface of the display, it can not only show an image, but also show three-dimensional structure. You may be able to touch it and feel the texture or three-dimensional structure. So these are all made possible with the new materials. And then we started to, we also have a program in the group developing sensors. I mentioned the one sensor, the electrophysiology sensor that was using conductive polymer. And then this is another type of sensor we made recently. It's an ultra-conformable skin sensor. Basically, what we want to do is to be able to get the detailed movement of the finger and the movement of the arm. And then, so that then if you think about virtual reality and then the person or digital twins, you want to get the detailed movement and location of the finger. Then potentially, if you try to do that with conventional sensors, each of the joint, you will have to have sensors to know the movement of the joint. But we take advantage of the material we develop. So we just spray on. So what you're seeing is one sensor, actually just a strain sensor. We spray on this biocompatible nanomaterial ink. And then the movement will cause the conductivity change. But this sensor is so conformed to the finger. There's no substrate. So it fits in every little wrinkle on the fingertip. So we can train the algorithm to learn the different resistance pattern correspond to the different movement. And then when there's individual using this sensor, we just spray on, and we have the general algorithm. And then we just have the user touch the object it's touching, then it will be able to, just a few strokes to calibrate essentially, that the software would be able to recognize what it's touching, like the shape of the object, and then we can train also, this is typing. This is a virtual keyboard. We just have 2 fingers only, and then you just train a few times, and then it can recognize the words with more than 90% accuracy, just with a few strokes of training. So this can be applied to any parts of the body, even though camera can be used to get the movement. But for the fine movement, or if the person is wearing clothing, we have people who are doing sports and like rowing, they want to get the detailed movement of the back. And then you won't be able to see very clearly under clothing. And then these are the areas that this could be very applicable. And then we also have, these are some sensors that we develop that has electrodes, that conductive soft electrode that we develop in the group that can give us the right adhesion to put onto these mouse. Actually, we are doing continuous electrical stimulation to stimulate the wounded area on the mouse. And we wanted to previously, the doctors do these experiments with wires. They can only do wound. It's known that electrical stimulation can help to accelerate wound healing, but they couldn't stimulate for extended time. So they want to know if there's continuous stimulation, whether it can reduce the scar formation, and also whether it can reduce the infection, and what kind of cells will migrate, and what kind of genes get upregulated. So all of those were difficult to study before, and also animal model was even harder. If you have wires, animals will chew on the wires. So we combine our material with these design wireless stimulation, that we could perform these stimulation continuously for a month. And then we prove for the first time that indeed this method can reduce infection, can reduce scar formation, and we know now what kind of genes get upregulated. So then this could kind of set the basis for the foundation basis, scientific basis for actually using these devices for future chronic wound healing. An area we are very interested in and quite passionate about is to develop wearables that can treat or monitor, and also allow methods for more precise, personalized methods for mental health treatment. And there, this is a project we have been working on for 5-6 years already with psychiatrists in Stanford to build such a wearable. And the biggest, well, there are heart rate variability. These are already available. The harder part that's not available that the psychiatrist would want to have is, one is skin conductance that requires direct contact with skin. And there are a few commercial sources that sell watches that can measure skin conductance, but then they are based on just big stainless steel metal electrode. They don't contact well with the skin. So to measure skin conductance accurately really require good contact with skin. So that's something we have developed in the group. And then another key biomarker that's needed is cortisol. That's a stress biomarker, and serotonin, that's kind of determines many of the pathway that's related to depression. So we want to measure these from either sweat or interstitial fluid. So now we have our first version. Now we are starting to test on human to see the first to validate the accuracy, and then we are going to use them for more studies to see if there's any correlation from what we measure here in terms of the patterns of these different parameters to different subtype of depression, so that the doctor can prescribe the right medication for depression patient. And then more further away type of work we're doing, taking advantage of the sensors and the electronics we're developing, is to develop these neurotransmitter sensors that can allow us to simultaneously electrically stimulate and also measure, for example, dopamine regulates the reward and also addiction. So we want to be able to see whether we can have probes that are suitable for long-term usage as well as have minimum invasiveness. And then also probes for the guts, because the intestine I mentioned earlier, actually 90% of serotonin is actually generated in our guts. And that can diffuse into the bloodstream and then get to our brain and impact our mental state. So understanding, and currently there's actually no way to measure serotonin inside the gut. So we developed these soft, we call NeuroString, that can measure simultaneously in the brain. So this is the first such experiment that's ever done in a weak animal. We have a neural probe that's implanted in the brain. Simultaneously, there is a probe coming out from the backside that's actually put into the intestine of the awake mouse. Then we can simultaneously measure these signals and then start to understand how these signals regulate each other. So that's very much the direction we're moving towards. And one thing really unique about what the capability we have developed now that will, I think, allow us to build more complex sensing systems is that I mentioned all the materials we try to develop, semiconductor, conductors, dielectric material. So now we actually have the capability to make integrated circuits that are kind of the new form factor, as I described, like human skin. And with our understanding of the materials and fabrication, now we're keep pushing the speed of these devices and density of the devices. To those working in semiconductor industry, this density and speed probably is really nothing, but these kind of capability at amorphous silicon level, for example, would be close to megahertz speed. And then the polysilicon level, we demonstrated more than higher megahertz level switching speed. So they will be great for electronic integrated circuit that's right next to the sensing front that allows us to amplify very weak signal from the sensors and also digitize the signal right at where the sensors are, because we are going to distribute sensors over large area, and the sensors are going to be very high resolution, very small. So that means the signal is going to be weak. So we will need this integrated circuit right at the sensing front. So now we have these already, at least the proof of concept developed. So we're very excited to integrate them. On the commercial side, to pushing these inventions to commercial side, then we have to think about in the lab, we work on very far out type of applications. And then we also at the same time want to take our inventions to commercializations. And then our first development was sensors that sense the human touch. So one of the products that we are developing is by Paramus, this continuous blood pressure monitor that's based on the sensor we invented from the lab. The first product is for infant monitoring. We're waiting for the FDA approval right now, so hopefully we can deploy it into the hospital in the near future. I also want to, Richard mentioned that we have the Stanford Wearable Electronics Initiative. I want to mention that we have, in Stanford, we really have a community working on different aspects of developing sensing technologies and also human-machine interface, and also understand how these hardware combined with software data science, how they can be used for health, understand human performance, understand how we can use them to control robot or make a robot more intelligent. So there are a variety of different kinds of research that's ongoing in Stanford. So eWare is really meant to gather the community together and have them interact with each other, and also interact with industry as well. And then another new initiative that I'm chairing right now, actually just got launched this year, that may be of interest to this group as well. It's called Taiwan Science and Technology Hub at Stanford. It's a donation that's from the Taiwan Science and Technology Council. And with this, now we are setting up this program in Stanford, and it's going to be bi-directional interaction. And this is not just with Taiwan. We actually want anybody who are interested in the Bay Area to work, kind of have interest to work with Taiwan, that this is kind of the hub that aim to help to build this connection. So our keywords are connecting, enabling, and empowering. So that's our role. And we are going to have fellowship programs for academic, for postdocs to come from Taiwan to Stanford, but we will also have entrepreneurs come from Taiwan to learn about the ecosystem, interact with people in the Bay Area, and be incorporated into the general Bay Area ecosystem. And then we are going to do a lot of networking. We just had the open house yesterday, and it's we welcome everybody who is interested in kind of have visit or collaboration with Taiwan. Everybody is welcome. So with that, I'll just stop here and be happy to answer any questions and have a discussion. Thank you.
That's great, Zhenan. Please stay right there, because we'd love to ask a question or two. We've got a number of people who are really very much into this space. And so I feel like I should kind of step back and let some of our guests ask questions first. Jack, how about you?
Yes, I'm.
Oh, wait, microphone coming.
I'm Jack Mormon from Beach Bay Advisors. Terrific, Professor Bao. I recall your presentation some years ago at Triple Ring Technologies, and you've made fantastic progress since then. It's very impressive. So I was wondering, so the next higher bar, if you will, is the aging population, and the diseases, of course, that are of most interest tend to be for that population. Skin is friable, dry, not so flexible. So how are you doing on making the wearable sensors for a tougher environment?
Mm-hmm. Well, tougher environment, I think that really depends on the exact use case. And many of the main part that the electronics is interacting with the skin would be the substrate. And the substrate would be most important. Also, it will have the role of encapsulation of the electronic devices. So frequently when companies ask me what are the opportunities, then I always say that substrate and the encapsulation, those are actually the larger volume of materials needed. And regardless of which kind of electronics will be incorporated, then we always need those. And then my electronic material actually is only less than 1 micron, maybe hundreds of nanometers in thickness. So majority is actually the rest of the material. Yeah, so that's I think just choose the right interfacing material and adhesives, and those are the important part that directly interact with human body.
Thank you. Zhenan, if I could ask, especially for this audience, so there's so much kind of sense of technology competition in semiconductors, regular semiconductor areas. Is it reaching this kind of wearable electronics, this kind of, like soft ICs? Is that part of the CHIPS Act? Are you seeing a lot of kind of increasing competition and making it harder to cooperate across borders?
Yeah, the CHIPS Act has majority of it, from my understanding, talking to some colleagues who are serving on the committee for CHIPS Act, is that its majority is to bring the silicon industry manufacturing back to the US. And for the research piece, there is kind of some bullet point about bioelectronics or something to do with human health, but it's very small, just a few bullet points out of the longer list. Yeah, so it's disappointing for research community because it's not much actually on the the research for next kind of future electronics, maybe a little bit for 2D electronics, a little bit for bioelectronics.
Okay, and probably the last question, I'm afraid, is going to be, how can people get involved with eWare, especially companies that might have an interest in supporting some of your research, or I think there's a public program happening this September.
Yeah. So eWare has a membership program. Company can either join our membership to get to know the bigger community. And we have seminars, semi-annual symposium, and also facilitated discussions with various faculty. And if you're interested in a particular topic of research and want to collaborate, feel free to reach out to us. Here, there's the website, eware.stanford.edu. You can contact myself. Also, I don't have the email, but on the website, the executive director, Angela McIntyre, is someone who helps to connect company members with professors and students.
And in the best spirit of Stanford, we would be happy to forward anybody's message over to Angela and make sure that you have a chance to get introduced to them. Also, Laura Smoliar is in charge of the Taiwan S&T Hub. Laura's a good contact of ours from a long time back.
Right,
We have to
that's
forward messages to her about the Taiwan program.
That's right.
So let us know, Ellen John, right, also.
Alan is the program manager.
The program manager. So I know that you worked this in despite having a very tight meeting you have to go to right after this. Thanks so much for coming over.
Thanks so much
and
for having me.
So I'm looking to kind of give you an update of what's going on at the center this year. We've had a very active year. What we're doing in the meeting today, I will do this for about 30 minutes, probably 20 minutes, and then maybe 10 minutes for Q&A. We'll take a quick break, and then we'll have our presentations by some of our visiting scholars. We've been around for 30 years now. This is our 30th anniversary. So we started out in Stanford's electrical engineering department with a very large US Air Force grant about industry and technology management training program for American scientists and engineers, specific to be able to either cooperate with or compete against Japan. And we immediately started our seminar series, our fall seminars that a lot of you know about already, and some other Stanford courses that are still going on. We brought in a lot of new information about Japanese technology developments. We also were very early using digital communications. We started video conferences with Japan and other countries back in 1994 with an old Polycom system, right? That was really funky. So this kind of thing with Zoom is just heaven, right? We shifted our focus to innovation. As the internet grew, the ease with which you could get access to information just really took off. It was easy to get information about what was going on in Japan and Asia, but much more difficult to understand what it meant. And so that's the difference between really technology development and the kind of things you need to do for technology management. So we shifted our focus to management of innovation. And we expanded our focus to Asia in the year 2000. I want to say this was something I saw in advance because as the internet took over, why wouldn't the same kind of network topology take over away from US Japan and US China and US Korea and US whatever, and have more of a kind of integrated things going on across the Pacific. So that's why we did this. We cruised along with mostly industry support since year 2000, but we were officially approved to be an industry affiliates program with member companies in 2017. And in that process, we moved from the electrical engineering department to the Center for East Asian Studies inside Stanford Global Studies program. So that means that now our primary financial support comes from member companies. This covers everything, including our salaries and operations. We provide some money back into the infrastructure for Stanford. And we're doing research, education, and outreach. Our research is really in three areas now: the impact of new technologies on industry value chains, open innovation management, and regional innovation systems. So of course, we're providing various knowledge exchange benefits to our member companies. We also do classes for Stanford students, and we remain committed to being a resource for Silicon Valley and the world in general for the public. So right now, as of today, we have 15 member companies, and you see that most of them are from Japan. We are also happy to say that we have 4 companies currently in process whose membership is either being reviewed by Stanford, their membership application is either being reviewed by Stanford or has been approved, but the final contract hasn't been finished yet. As you see, we have 1, 2, 3, 4, 5, 6, 7 visiting scholars from our member companies, and we have 2 additional visiting scholars who are coming in on special grounds. So first is Professor Michiko Ashizawa, who is on her way to the Keio Business School, and she will be our first visiting scholar presentation. And also Mr. Shinichi Ogawa, who is a Fulbright visiting scholar with us this year. So our knowledge exchange is divided into 3 kind of types. There's things that we target for our member companies, regular meetings, sharing of information by email, visits to member companies, and also we try to take care of our members when we do our public programs and get comp tickets whenever we can and so forth. For the Stanford community, we're still developing courses, and we'll show our seminar series that we're probably best known for. And our public outreach is not only what we're doing here at Stanford, but some big programs that we're doing in conjunction with other organizations and meetings and presentations that we give all over. So for our member company regular meetings, we kind of have been doing these about once a month, but we're probably going to shift back to more like once every 2 months or once a quarter. We did a series of 3 sessions on a published case study from Harvard about Honda innovations. And the third and final session, we had Nick, Mr. Tsukimoto, who is the CEO of Honda Innovations, come and be with us in our meeting. We also, because of the economic situation, even before Silicon Valley Bank, we had a panel of venture capitalists who came and talked to us about opportunities in the downturn, what investors are looking for in 2023. So we try to stay on the leading edge of these waves. Our autumn seminars this past year were on new business in Asia driven by climate tech and sustainability. This is not only an important topic, it's a very timely topic. And you can see that we were able to bring in presenters from India, from Japan, people who are active in Singapore, people who are active in Hong Kong, and some other things that are going on. In the spring, we are right in the middle. Actually, we just finished the next to the last session in our spring quarter series, which every year is about the newest trends in entrepreneurship in Asian high-tech industries. And again, we were very happy to have speakers from China, from Singapore, Jakarta, from Japan, from Korea, and we've had a company come in from Hong Kong. We're very committed to trying to keep up with the whole breadth of what's going on in the major Asia economies. For the university courses, one thing that we did that's kind of unusual is I'm joint teaching a course with Dr. Amit Kapoor this year, which we taught in winter on rebalancing economic systems. Unfortunately, the industrial revolution that we're in has led to great inequality, and it's led to a lot of social problems. And if we don't do something about our economic systems, we may well have the kind of bad outcomes that happened after the first 2 industrial revolutions, which led to a couple of world wars and various kinds of autocracy. Dr. Kapoor is a very special person. He's someone that I've known for about 10 years now, since we were together at the global meeting on councils of competitiveness. He represents India. And he is adjunct faculty at the Harvard Business School. He's the chair of the Porter Prize for India. And just this week, he has been named one of the 7 top economists in India. So quite happy to be working with him on that. And in cooperation with his Institute for Competitiveness in India, we put on a 2.5-day meeting in February that we called the India Dialogue. We had over 40 speakers, including about 25 or 26 who came from India. We had a Deputy Assistant Secretary of State and a senior person from US-AID speaking. As you see in one of the pictures, the Minister of Health gave remarks from India. The Chief Economic Advisor to the Prime Minister was in our conference. And John Chambers gave us a fireside chat at the VIP dinner. So we're very happy to be involved with that. And this is now a kickoff to a continuing program. We're going to do the yearly summit. It will be invitation only, but if you're here, send me a note and you can probably get in. So we also have started a monthly online webinar, and the next one is tomorrow morning. This picture in the bottom right is our speaker tomorrow is a member of parliament, and his topic is getting to the green frontier, net zero development model for India. So we're excited to be doing this. We've got 16 working papers that are already up on the website, and an email discussion group. We would be happy to have you join. And yeah, there's an easy way to get into it from our website. We also cooperate with Japan Society of Northern California every year to put on the Japan-US Innovation Awards. We're in the thick of this now. Our next meeting will be July 20th, 2023. This past year, we gave Emerging Leader Awards to Tier 4, which has kind of the operating system software for autonomous vehicles. And Databricks, which is well known in the AI development community. Professor Mentaid, who is one of the founders and is, I think, CTO or Chief Science Officer for Databricks, came in and spoke in our program. We also give out awards to 5 exceptional Japanese startup companies that we think will be interesting for Silicon Valley. And we cooperated with Keizai Silicon Valley to help put on their New Year's reception. So this year, before they got this crazy idea about moving to Las Vegas, we were able to have the president of the Oakland A's be our keynote speaker. And it was a very good time. He was a great speaker. Just a few numbers so you see how we have involvement. We're not getting as many students registered for our courses as we used to. We used to have well over 150 registrants of students in these seminars. Part of it is just the proliferation of seminars. So now we're down to the group that's really interested in what we have. But we do have quite a few Zoom registrations for each one of our programs, and they come from all over the world. And we're getting quite a few people from the community now that we're back fully in person again. At the India Dialogue, we had about 225 people registered, and we've already had almost 3,000 YouTube views of the videos of some of the sessions that we did. So other things I think that I should mention is that we get an awful lot of visitors, especially now that travel has kicked back in. This picture over to the right is the mayor of Sendai, who led a delegation of 12 startup companies from the city of Sendai that was organized by JETRO primarily and kind of supported by the US Market Access Center here. So we've had people from just about all over Asia, usually about 2 groups like this a week. So we're definitely one of the scenic spots in Silicon Valley now. Some more pictures from this. We had visitors from Suzuki Motor Corporation's Innovation Center in India. I had visitors from Waseda University in January, and the US Consul General in Osaka, Japan, put together a group of entrepreneurs from the Osaka area to come to the United States. So it's not just the Japanese government that's supporting international activities by entrepreneurs. The US government is doing this too. I travel a lot. Usually in fact, I have been able to do all of my business travel with other sponsors so that our member companies have not been charged for my travel expenses. That's something that is kind of good, but we can't always rely on. I was able to give 8 presentations at different member companies this past year. I had a dinner with some of our former visiting scholars, and a lot of this involves, pretty big speeches. So the picture there is the Zero Emissions Technology Summit in Kyoto that had more than 1,000 people in attendance. The day before that, I spoke in a major conference of the life insurance industry in Tokyo and to a science policy fellows symposium in Okinawa 2 days before that. So these trips tend to be pretty packed. Here's a few more pictures. Only in Japan. You have to have hard hats and also slippers, right? So this is a synchrotron that's being built at Tohoku University. And I visited Suzuki Motor Corp, kind of an exchange visit to their visit here. And this was the dinner we had with some former visiting scholars in Tokyo. So what we're planning for this next year, I think that the big picture is always the hardest to see. And so I want to look at the emerging digital economy in context. We'll try to keep a good balance between the technology developments, but also the policy and business and social developments that surround it. So we're going to look at topics like technology standards, generative AI regulations, which are emerging, data governance, the impact of reshoring policies like the CHIPS Act, labor force challenges, patterns of open innovation, omni-channel, where it's not just digital economy, how do you connect online and offline retailing, for instance, business models, and international joint development teams and so forth. So I'm looking forward to putting this together. It should be a great series this fall. I'm going to go back and teach the Japanese Business Culture and Systems course that now that I'm teaching this new course on rebalancing economic systems, it's gone to once every 2 years, and the rebalancing course will go once every 2 years. And we want to sponsor MIT, Dr. Kapoor, to be a visiting lecturer to teach a new course on innovation and competitiveness, perspectives from Asia. In the spring, we'll do the entrepreneurship series again and look at the newest trends and outflows. And I think that to understand who we are and what we do, we're very interested in how to make sense of a very confusing situation. And every industrial revolution always has a lot of noise in the signal. So we're looking at developments that will impact the current uncertain economic climate, new technologies and their impact, open innovation patterns and best practices in innovation management, and yes, the impact of geopolitical tension, especially on business innovation. We're going to continue our cooperation with our current partners for our major programs, and especially we want to keep building on the India dialogue. India has been underserved recently, and we want to kind of address that. And as always, we'll maintain close relationships with our member companies. We're going to continue our regular meetings and visits and presentations, and would always be happy to hear solicitations of your interest in particular topics. You're our friends. Thank you for coming to our annual meeting. And so any of you, whenever you see something you would really like to see something about, we would be delighted to hear from you.